Good afternoon, everyone. My name is Rishad Shafiq, and in the next few minutes, I'll be basically presenting these slides online, unfortunately, because of the circumstances that we have from our side. This paper is a joint effort by Dave, Danius, Isa, myself, Siddharth from ARM, and also from Alex within the Microsystems Research Group of Newcastle University. The basic idea of this paper is based on using using significance of data for controlling the approximation of computing and thereby achieving energy efficiency. So I will be basically now, in the beginning, I'll be talking about some issues about why we think approximate computing is important. Then I'll be talking about why and how we are going to infer the significance, which is what we intend to use for controlling the approximation in computing. I'll also be showing an approach typically applied in a case study of an image processing application, and finishing with ongoing research and conclusions. So there had been a good number of presentations in the past talking about approximate computing and the needs of approximate computing in very many ways. But the kind of views we have about approximate computing is this. There are four basic issues that surface around approximate computing. We want more performance with less amount of power, and possibly also using less amount of logic. So one way to do it is by pruning your circuits in favor of more performance and less power, and losing a little bit of quality. That's why approximate computing is in here. And lately, of course, we have a growing need of using computing systems that are power adaptive, that can adapt to incoming powers, or that can even adapt to outgoing powers as well. If you have to control your power based on your needs, you have to have some level of control on the algorithms or circuits or subsystems that you use. And I'll also highlight the fact that by using power adaptive systems, what you'll eventually generate is something called intelligent ubiquitous computing, which are being run by, let's say, harvested energy. Because the energy is limited, you'll have to find a way to adapt to the incoming power at all times, and approximate computing can be extremely handy for these circumstances. And of course, sometimes you need to compute over a large dynamic range of power, and that's where you can create approximate computing levers in such a way that you can pretty much operate on a large domain of power without actually failing on the functionality, essentially also surviving for very many power envelope variations that you have. Now, traditionally, approximate computing had either been either an issue of the software community, who would be interested in finding out, let's say, for a given application software and a given algorithm, can we find different alternatives of the same algorithm? In this case, the example is drawing on, let's say, convolution filtering algorithm using different filter size and kernels. On the other hand, there is another community who is on the hardware side, who basically profess that, okay, whatever the application software is, we can process the application using either precise set of hardware, such as precise multiplier, or imprecise hardwares, such as approximate multipliers. So essentially what you will be doing is if you were to control both software and hardware under one common platform, you'll be controlling the energy quality trade-offs within one domain. And that is exactly the whole idea about this paper. We'll be using significance from the application and also the application data to govern the hardware and software knobs in one place. I'll be showing a minimalistic kind of case study here, but we have works going on in this direction for some time now. Now, image processing makes a great example of big data applications. I'm sure some of you will have already known what big data applications really are. What they do is basically, because they have access to, let's say, sensing subsystems or some data generation subsystems, they keep on generating data one after the other. Sometimes, especially for image processing applications, you keep on generating data which are not necessarily generating new information at all. So what it means in the existing platform is that because we process data ignoring the informational value or worth, so we keep on burning joules after joules without actually realizing that these joules are actually meaningless to the point of point of information. So this is a graph which basically motivates our research. So what it basically says is that as you go on using higher and higher resolutions, so as you can see, over a 24-hour period, the amount of energy that you burn for 15 frames per second or even 30 frames per second sensing subsystem will eventually be in the order of, let's say, 75 megajoules or so. This is a lot of energy. So the question is, how can we reduce the energy? What are the opportunities for reducing this energy? As I showed you before, that one of the opportunities is to use significance or informational worth of data to basically govern the computing. The basic idea is that if the data is less significant, use less resources and thereby consume less energy, which obviously will be less accurate. And if you have more significant data, you should allocate more resources, essentially having slightly more energy, but of course you get better quality of outcomes. So what you essentially want to do is to control the quality and also performance within a certain given required values. So if that becomes the problem, then we pretty much can govern these things dynamically and during runtime. So while looking for the ways to define significance, we came up with a good number of literatures, and we found out this fantastic paper from Nature Reviews Neuroscience, written by E.T. and Koch. They were basically finding out ways how humans perceive significance or attention details to a certain image over time. So what they came up with is this: the human attention is largely dependent on the differences present in images. So if you see on this left-hand side, we have a beautiful Lena posing for you, obviously. And on the right-hand side, you will see the black blobs basically telling you that these are areas where the differences are low. So, and the white areas are the ones which basically shows these are the areas where you have higher differences. And if you think about it carefully, and if you look at the images on the left, you will actually see that your level of attention will basically be circumfacing the areas where you have a lot of contrast, a lot of variance as such. That led to our research in finding out why and how we should define significance. So what we did is we took an image, we found out a way of splitting that image into multiple blocks of images. Then we used a little software tool to basically use different algorithms to control their masking of standard deviation, mean value, and also derivative values in very many ways. So we came up with four different kinds of algorithms of finding out how we define significance or variance within the images. The first one being the derivative method. That means you find out the derivative of each and every pixel that you have in your image, and then you will be masking them with the standard mean. The second one, which is the method 2, is the standard deviation mask. That means you just take the local mean and then you mask them with the global mean in some way. And then you come up with another method called derivative mask. That means you just do not compute the mean at all. You take each and every pixel, but you mask them with a constant value somehow anyway. And there is also this mean masked value. That is basically you just take the global mean and you just take the local mean, and you then find out a kind of masking between them somehow. Unfortunately, while looking at these definitions, we found out that whether you do the derivative one or you do the standard deviation masked one, the amount of time you spend for computing significance is quite significant. In the case of, for example, a 20 megapixel image, you're looking at something in the order of 180 milliseconds for method 1, or even 160 milliseconds for method 2, and that's not good, because you don't have to spend so much time for a real-time application looking into the significance. So what we did come up with is that, okay, we don't need to be so accurate in finding out the significance. We can be rather approximate. So what we can do is we can select some 4 random points. These random points can be selected in a quasi-random way to essentially give me 4 different points whereby I can find out the standard, absolute standard deviation masked by the global mean. That is good enough. As you can see on the bottom right corner, this image, which is defined by the approximate method, is already good enough. And the good thing is that it only takes 4 milliseconds, which is compared to 180 orders of magnitude lower than the other ones. Now, so using that, we started developing a really adaptive approximate computing paradigm. So the basic idea is that you keep on acquiring real images over time. For each image, you create some blocks out of these things, and each block will be processed by a kernel, which we designed, OpenCL kernel, which looks at the approximate standard mean master significance inference, and we use that to govern the computation. So basically, this is going to be this is another OpenCL runtime we developed. What it means is that if you have found a block which is significant, use precise processing, and if you have found a block which is not significant, which is 0, for example, then you use approximate computing. So by using approximate computing on top of the precise processing, what it means is that you have the opportunity for some of the parallel blocks. You have the opportunity of using DVFS to claim back your slack, essentially also reducing the energy. And then once you're done with that, what you do is you go back and find out, okay, have I done good enough in terms of reducing? I've done good enough in terms of reducing energy, but have I done good enough in terms of reducing the quality to a point which is acceptable? If you are, for example, if you have done it, if your performance is overly optimistic, so what you want to do is you want to extract more significance, more insignificance. And if you're overly pessimistic, that means you have done too bad a job, so you want to extract more significance. So this is something you can do using a very simple learning algorithm, which I will be showing afterwards. So the concept of one of the things we have done in the process of doing this is the way that we estimate the PSNR, or the quality. Traditionally, in order to estimate the quality, you have to really follow a certain procedure of using software and hardware kind of algorithms to determine what kind of effect you have on the quality. But we completely bypassed those complicated hardware or software routines by doing something simple like this. So we have, let's say, a set of parallel image blocks with significance information, 1 meaning significant and 0 meaning not significant. So we already know, we have already pre-characterized the impact of, let's say, using, assigning 0, the insignificant blocks to, let's say, approximate computing, and the impact of using 1s on the precise computing. So what we can do is we can aggregate the noise from individual blocks and eventually find out the overall PSNR of this, completely bypassing any additional software or hardware algorithms. That is a great advantage that we have from our approach. So, as I said, there is also a little bit of learning involved. So let's say when you have a certain threshold TM, you want to continue using that particular TM. And once you use that TM, unfortunately, there is an arrow which is missing right here. So once you have, let's say, you continue using this TM, then you want to check out whether you're happy with this quality that you have generated from the system. If the quality is good, you continue using that one. If the quality is not good, then you have to basically ask the question, okay, am I overdoing things? Am I too pessimistic? If I'm too pessimistic, then I'll obviously have to increase my threshold, which will eventually reduce the number of significant blocks and eventually increase the number of insignificant blocks. On the other hand, if it is, if I'm underperforming in terms of quality, so I have to decrease the threshold to some extent. And this increasing and decreasing can be a continuous learning process rather than a static learning process. And this we have done really fantastically in our OpenCL runtime. Now, moving on, using the case study of image processing application, we developed, let's say, an image convolution filter, 2 different filters, the precise one being 5x5 image processing filter, and the approximate one being 3x3 convolution filter. So the idea is that if a certain block is 1, meaning significant, we use the 5x5 kernel, and if the block is approximate, then we use 3x3 kernel. Obviously, this will give me an opportunity of doing DVFS for reclaiming my slack later on. The point from that is basically explained in this diagram as well. As you can see, if you increase the workload for 5x5 on the right hand side at the bottom, So if you increase the workload on the right hand side, your latency will start to increase, but obviously this latency will increase further if you start reducing the frequency as well. On the other hand, if you use the 3x3, likewise the latencies are going to be slightly lower compared to the 5x5, and of course if you reduce the frequencies, the latencies will be again increasing linearly. But of course, the highest latency for 3x3 is quite low compared to the 5x5 one. Okay, so now on the quality side, which is also very important to understand, that on the quality side, if your reference for the conversion filter is really 5x5, so that means if you do 100% 5x5, that is your reference. And if you use some of them, if you deduce some of them, and if you discount some of them, and if you use, let's say 3x3, then of course your quality will start to go down. But as you can see, the quality can only go down so much, and the interpretation of quality on visually from these diagrams is very hard to tell that how much degradation has really gone on. Now, so that gives an opportunity, because you're using more on the right hand side, you're using more approximate units in parallel, so that gives you an opportunity of doing DVFS for some of the shader cores and GPU cores on the right hand side. So on the bottom left, we have the diagram for let's say the energy trade-off for different kinds of algorithms that we have developed. The first two, the set of diagrams, are basically the significance agnostic traditional approaches using fixed GPU frequencies of 600 and 300 megahertz each. And on the right hand, on the third one for each diagram will be the proposed significance driven one, and the different bars basically show the different resolutions that we have tried for. And you can very much see that for different steps in the algorithm that we have for step 1, step 2, step 3, and step 4, step 5, the major contributor almost all the time major contributors are step 1 and also step 3, and rest of the ones are basically really minor. And the proposed approach, the significance driven approach, benefits from energy savings because it does two things. First of all, it uses approximate kernels, and secondly, it also uses DVFS dynamically. And thirdly, because there is a quality requirement, it is always trying to meet the quality requirement to maximize the energy savings as much as possible. On the right hand side, the same trade-off has been depicted as well, but in this case in terms of latency. As you can see, as you go on using let's say lower frequency and also more approximate ones with DVFS, obviously your latency will be affected to a point which is only acceptable in terms of performance. Now, this is a work that we had been doing for some time, and we had been designing our own trans-precision GPUs. The GPUs will have a hardware significance inference engine built in. That is the idea, and we are developing it at the moment. There's a lot of memory issues that we are facing at the moment, and we are solving them as we speak. And then we are also developing hardware and software control knobs for us to use in our programming environment. The basic idea is to develop an OpenCL based runtime for further application agnostic PEC trade-off controls, and eventually using a machine learning based middleware for significant inference completely out of the scratch. As you can see, the 6 millisecond overhead that we have can still be further minimized by using hardware completely. This is a joint work again. If you have any questions, you can always ask me directly at this email address. However, if you want to, if you'd like to discuss further, you can also copy in your email Dave Burke. You can just search up Dave Burke Newcastle. You'll find out his email address right away. Thank you very much for your time, and I really appreciate you being with me throughout this period. And I would very much appreciate if you still send out any questions that you may have. Thank you very much indeed.